on this Warsaw Astronomical Observatory Tuesday seminar. Today we have a pleasure to host Maciek Wielgus. Maciek did his PhD at the Warsaw University of Technology on adaptive decomposition and analytic signal concept in the interferometric fringe pattern analysis. He then moved to Harvard to work in the Black Hole Initiative, and now he works in as a postdoc in the Max Planck Institute for Radio Astronomy in Bonn, Germany. Maciek is an author of over 100 publications, mostly on very exotic objects such as black holes or even wormholes. And he's also a member of the Event Horizon Telescope project. And today we will hear about EHT observations of Sagittarius A star. Maciek, the floor is yours.
Thank you very much. It's a great pleasure to talk to you today. I've been many times at the talks here. I don't think I had a pleasure to give a talk in this room. I will assume that you hear me and that you see my slides so that the technicalities are okay. And let's see if I can change the slide with a clicker. Oh my gosh, everything works. Okay, so let me start with this image. This is a kind of a large-scale image in low radio frequencies toward the galactic center. This is my second favorite image of the galactic center released in the year 2022. The image is from the MPIRA array, and it's showing the spectral index map. So you can see what a diverse environment it is, what a hot mess it is, how different locations correspond to different physical properties. And what we are after is this region here. This is the dynamical center of our galaxy. And in particular, deep under the level of a single pixel of this image, there is this image, my favorite image of galactic center released in 2022. So it's really a tiny feature. It's about 50 microarc seconds of angle, corresponding to a couple of square degrees of this large scale image. So in order to get this sort of crazy resolution, I will talk about the special instruments we needed to develop. But let's just look for one more minute at arc-minute scale. So this is the scale of this Sagittarius A feature, not Sagittarius A star. This is arc-minute scale, and you can see also in this small region, it's also a very diverse environment. I will draw your attention to this feature that is referred to as mini spiral. It is a gas slowly trickling into the galactic center in this bunch of spiral arms. This is a 3D structure. Let me also draw your attention to this clockwise stellar system. This is where Wolf-Rayet heavy stars live. They blow a lot of winds, and we believe that this wind from Wolf-Rayet stars in this purple feature, the clockwise stellar system, could actually give the most of the matter that is accreting onto the Sagittarius A star. And inside, deep inside, there is this cluster of S2 stars that we are probing in infrared with gravity, with Keck instrument. This is the famous S2 star orbit, and deep inside of this mess, there is this compact object that we call Sagittarius A star. And there is a long story, a beautiful history of science of how we got from first detection of this compact source all the way to the resolved image. So I will let's say that I will call this a culmination of these decades of study of Sagittarius A star. And this would make a pretty interesting story about the history of science to go through these different steps. But this is not the talk I am giving today, so I will not spend much more time on the history of the observations of Sagittarius A star. Let me just mention something that happened before 1974, before the first detection of Sagittarius A star. Sometime in 1960s, astronomers accepted the idea that quasars are powered by the supermassive black holes. And sometime in the 60s, Lynden Bell proposed that perhaps it's not just quasars, perhaps all the galaxies, maybe they were quasars once, and now they have some burnt out cores in their center. So maybe we should be looking for supermassive black holes in all the galaxies, in particular, why not in our Milky Way? So when in 1960s, people did a little bit of a hunt to search for a compact radio source in the galactic center, but you saw what a hot mess it is in one of the previous slides. There is a lot of features, and Sagittarius A star is not particularly bright, actually. In terms of volumetric luminosity, it is about 100 stars, 100 suns. So 100 suns for a supermassive black hole, it's not actually super impressive. It's not an AGN source, nothing like that. So it was a problem. People didn't have the resolution. They needed to develop techniques to get sufficient resolution to constrain a compact, bright radio source. And that only happened after a few years of many attempts in 1974. So in 1974, there was this discovery. There is a compact source in the galactic center. It corresponds, it's as close as we could measure to the dynamical center of the Milky Way. It wasn't named Sagittarius A star yet in 1974. It was only named Sag A star in this paper in 1982. And this paper is very interesting for pretty much two reasons, not just one reason. One is the introduction of the name and this star that is borrowed from chemistry, borrowed from the denotation of an active, excited element. But also for the interpretation. So people were working in this frame of mind of quasar remnants, and the structure of a mini spiral that I already pointed out to you on a previous slide, it was interpreted as a remnant of an outflow of sort of precessing jet feature that were seen before in quasars. That is not what this feature is. It's just cold gas trickling slowly toward the galactic center, but that supported the idea that there is this supermassive black hole in the center of this feature. So what kind of instrument we need to observe this very tiny compact source in the galactic center? Well, we only can do two things to increase our resolution because of the diffraction limit. We can go to short wavelengths and we can go to larger telescopes. So if we're earthbound, well, that's pretty much as large telescope as you can get. You can pretend that your Earth is a dish of a telescope and pretend that this telescope is just has a couple of locations of active surface. It's mostly empty radio dish with a couple of active pieces of surface. This technique that allows you to make this assumption and proceed and get data under this assumption is, well, generally interferometry, but specifically in this context, very long baseline interferometry, which means that the telescopes are not physically connected. So you have to record raw data. It's actually a lot of data. It's petabytes of data at each station, and you have to numerically perform correlation to get the interesting data components. But the structure of the EHT, Event Horizon Telescope Array, is somewhat more complicated. There are two sites that are themselves interferometric arrays. This is ALMA and SMA on the top of Mauna Kea. So those guys normally work as interferometers themselves. To get the data useful for Event Horizon Telescope, they have to forget what they were built to do, and they have to not try to correlate between different dishes. They have to sum up all the signal, pretend that they act as a single dish, and give all of this signal uncorrelated to compare with other stations of the Event Horizon Telescope. But astronomers are greedy by nature. If we can have more than one type of data, we want more than one type of data. So we engineered a pipeline to go around this phasing of ALMA and SMA and to give us light curves of Sagittarius A star and give us images of Sagittarius A star, but the ones seen by the ALMA array and the SMA array, so telescopes of hundreds of meters of aperture, and not telescopes of 10,000 kilometers of aperture, which is the EHD. And I will talk about light curves a little bit because I was responsible for the light curve part of the work of the Event Horizon Telescope. So I feel sentimental and I want to talk about light curves a little bit. So why study light curves? One big reason for that is the variability, the intrinsic variability of the source. If you recall, in 2019, we published images of M87. And now what I am talking about, a black hole in our galaxy, Sagittarius A star. Those guys are very different. They are different by the mass factor of 1,500, which means all the characteristic timescales are different by a factor of 1,500. So if GM over C square, the characteristic length scale in the system, C cube, characteristic time in the system is 9 hours for M87, the same characteristic time scale is about 20 seconds for Sagittarius A star. And this technique that we are using, the very long baseline interferometry, it relies on Earth rotation for the thing that we call aperture synthesis. So as the Earth rotates, we see a little different aspects of data as the observations progress. Which means we synthesize a single image from a couple of hours of observation. We have to wait for the Earth to rotate and give us more and more information. So it's now you see a clock. This is a human clock here, and you will see how, according to simulations, how much M87 changes in respective time, and how much do Sagittarius A star changes. And remember, our observations take a couple of hours to be finalized. So this is how much things change. You can see M87 barely moving. It's not really changing on a time scale of one night of observations. Sagittarius is changing as crazy. So it is a conceptual problem, an engineering problem, an algorithmic problem. How do we define a static image of Sagittarius in a proper way? And can we say that this image is a representative, a representative sample of the state of the source, of some average state of the source? So to summarize the data related aspects before I move on to light curve analysis, this is where we sample our data. In interferometry, you sample Fourier plane of the image. You don't sample directly image domain as you would do if you had an optical telescope and if you would take a snapshot of something. It's a little more complicated with interferometry. So you can see all the pairs of telescopes are giving us one line on the Fourier two-dimensional plane. They are line and not points because of the Earth rotation. So as Earth rotates, we move along these curves. Here you see the amplitude of the measured data. So there is an interesting thing to point out already in this amplitude plot. For the people who are very familiar with Fourier transform, they know immediately what is the Fourier transform of a ring. The Fourier transform of a ring is a J0 Bessel function. So here in this model, dashed line, I will say I fitted, but it's not an honest fit. It is just putting a model on the top of the data. So I use a model with just 3 degrees of freedom: total flux density, diameter of a ring, and how much it is blurred with a Gaussian function. And you can see that this model, with again 3 degrees of freedom, it is extremely simple model, matches this general property of the data. It's not a proof that the image has a ring-like morphology. We can still trick ourselves into that, but it's definitely a necessary condition that the model somehow represents the data properties. And here are the light curves that we extract from ALMA and SMA. Now, these light curves were used for the VLBI calibration, for the calibration of the Event Horizon Telescope data, actually in multiple ways. First of all, with our smart self-calibration of ALMA, we obtained instrumental gains of ALMA, which is tantamount to saying that we absolutely calibrated the most important component of our array. Then, because we have Apex telescope, which is at the same site as ALMA, it doesn't resolve the source on the baseline between ALMA and Apex, just 2 kilometers. It's not Earth-size baseline. We also get absolute calibration of Apex because we know the light curve and we know gains of ALMA. Then we have another pair of stations that are close to one another, JC and TSMA, which also do not resolve the source, so we only see a point source. And we know the light curve of this point source, so we absolutely calibrate this pair. We absolutely calibrate this pair, JC and TSMA, so we remove another amplitude gain degree of freedom. Then there was LMT, a huge dish, the largest single dish in our array, a 50-meter diameter dish in Mexico City, not city, Mexico, but definitely not in Mexico City. And this guy has a pointing problem because it's a huge dish. It's difficult to point it in the right direction. It has a very small beam. So it behaved very erratically in terms of amplitude gain. So we delivered priors for LMT, which means altogether we have calibrated 5 different stations out of 8 stations in the entire EHT array through the analysis of a light curve. It was a great success from the calibration point of view, but very small. I mentioned a problem of the variability of the source, and the idea that we had, how do we help to define a single image, was why don't we normalize VLBI data with the light curve? So we remove at least some amount of variability in the data, in the VLBI data. And we did that. I will not go into details of the procedures we used. It was a lot of work. I will only hint at a big volume of work by listing the papers in the EHT publication list from May this year, when we published Sagittarius A-star images, which ones are explicitly dealing with the variability. We published 10 papers, 5 of them explicitly tackle the problem of source variability. So like half of the work is to understand what's going on and how do we define VLBI image of a source that doesn't want to stand still for a couple of hours. Well, I guess I'll have to be clicking now. No, okay, it works again, sorry. Right, so what you're seeing here is the image of Sagittarius A-star as ALMA sees it. So this is not the resolution of Event Horizon Telescope, this is arc mirror scale. You can see this faint emission here is the mini spiral that I already mentioned a couple of times. And there is a time varying point source, what is point source for ALMA, but it's resolved on VLBI baselines. So this is from where we have these fine light curves, well-calibrated light curves of the compact source. And we have 3 days of such high-quality data with ALMA and SMA. These 2 days, we published images of VLBI source on these days, and it looked like that. This is drawn from the EHT publication. We didn't touch the last day. And the reason we didn't touch the last day is, first of all, an X-ray flare that was observed by ALMA just before the EHT observations. And second of all, we measured statistically that there is much more variability at millimeter wavelength on that day. So we decided that, okay, we're doing good thing here. Let's just publish the quiescent source and let's, stop and think what to do about the flaring source later. And we're still thinking what to do with the flaring source analysis, but we published the 2 days of quiescence with the VLBI. So, well, the reason we have doubts is, well, who can guarantee us that the morphology of a source is the same on quiescent time and during the flare? Maybe the source looks like that. That was kind of my artistic idea. X-ray flare is like an explosion, maybe. So maybe it should look like kind of atomic mushroom, or I don't know. We will know when we get to analysis of the VLBI data. So I will spend just a little bit of time talking about light curves. Again, the only reason to specifically talk more about light curves is because I led this work, so I want to talk about my stuff most of all. Using this opportunity of generating first images of the resolved source, we decided to do like a review of all millimeter light curves in the literature. So here you can see light curve from 2005 all the way to 2020, everything that we published in millimeter about Sagittarius A-star, and everything here shown as a bunch of histograms. Well, one thing you can immediately see, the source is not actually super variable at radio frequencies, right? It's like 3 Jansky plus minus 50%. It doesn't change by an order of magnitude like it does at X-ray or infrared frequencies. But you can also see that it appears that there is some kind of long time correlation in the flux density of Sagittarius, because during the HT observations in 2017, the source was very low, and it was very low a year after, a year before, and then historically it wasn't necessarily that low. So maybe there are really long timescale correlations in the source. Well, we want to study variability. We want to describe the variability of the source. One of the tools to do that, which I'm pretty sure this community is very familiar with, are structure functions. Structure functions are like PSD, but without Fourier transform. So they are kind of good for sparse sampling of data. One thing you can see immediately is that it's a red noise kind of spectrum, because there is more energy at lower frequencies or longer time scales. It grows with the time scale. Blue lines here correspond to individual days. Black line corresponds to all the data from 3 days analyzed together. So red noise, you can measure the slope. You can translate it to PSD slope of minus 2.6. You can see that we detect robust intrinsic variability, meaning variability that dominates the noise level. Noise level is denoted with gray curve here, on timescales as short as a minute. So really the source is extremely shaky. It changes on such short timescales as a single minute. There is a change of the slope at some point, and this is interesting for people to speculate about. People try to speculate about spin measurement and things like that. I will refrain from speculating at this point, but it's interesting that there is some change of slope persistently on time scale of 10, 20 minutes. Then there is a second one that we don't trust at all because of the sampling limitations. And I think that I already mentioned, on the day with a flare, on April 11, there is much more variability in the data. So the blue curve is far above the black curve. The black curve is the same in each of these panels. So it's much less variability on the quiescent days and much more variability on the day with a flare. So again, a motivation why we didn't yet publish the LBI results from the flaring day. And there is an interesting general comment about the variability. So of course we want to compare everything with models, with numerical models that we have. And we noticed that pretty much all the numerical models that we use overproduce variability. And should we worry about it? I think we should worry about it a bit. Our model do not reproduce the time-dependent properties of the data. Some theories started referring to this as variability crisis, which I think is a strong word, but it is a little bit worrying. Our numerical models are missing something and are generally too variable. Well, what more can we learn from light curves? For instance, we can get a spectral index. We see that we are near zero in terms of spectral index. So on our spectral energy distribution plot, we would be about the maximum, about the synchrotron maximum for this source. We can also resolve the spectral index in time. And this is interesting because spectral index is near zero for other days, and close to the flare, which is this red star here, it's negative. It only recovers on a time scale of hours. It goes back to around zero. So what does it mean? It could mean that there is something that is very optically thin emerging in the system, some new component in the system. In any case, this is an interesting constraint for people who try to understand the flaring activity of Sagittarius A star and try to model it. And when there are no delays across the ALMA band, why is it a positive information for us? Well, the reason is that if the source was a little bit optically thick, then it would probably, we would see a delay in those signals because the photosphere would be located at different location for different frequencies. If the source is optically thin, which is good, if we want to image the very innermost part of the source, we want it to be optically thin all the way to the event horizon, then it would not show the delays in the interband delays in ALMA signal. So it's good. It tells us, it's a suggestive indication that the source is indeed optically thin, and we could see the source all the way to the event horizon with the Event Horizon Telescope. And finally, what we can do with light curves is we can also compare the slope of a PSD, slope of the structure function. And what you see here, the histogram drawn with red is the histogram of the slope of the PSD, or really the slope of the spectral function, in all of the library of numerical models that we use to make comparisons to the data. And our measurements around here, and this is the popular model of damped random walk. So people use damped random walk because it's an easy model, a simple model to be used, but it doesn't reproduce the statistical property of Sagittarius A star. It's definitely more steep slope of PSD. This variability is more red noise-like than the damped random walk. So this is an interesting conclusion to make as well. And finally, the last thing I will tell you about in terms of light curve analysis, I will just mention a work that I led that was published in September this year, where we did make our first attempt to dive into April 11th and see the dynamical signatures on April 11th, on the day with the flare. And we saw, we interpreted variability of polarimetric signal from ALMA with an orbital model, a hotspot orbiting galactic center, similar to the models employed by gravity collaboration for the analysis of the infrared data. And we fitted this model to data, and we obtained following conclusions, that if the model is correct, that would imply 70 minutes period, radius of about 10 GM over 3 square, dominance of the vertical magnetic field, and low inclination of the source. Is it true? We don't know. It would be nice to see the analysis with the EHT and VLBI, but we have to wait for that. For now, what we have is the ALMA analysis hinting at the orbital motion after the flaring event. And a remark about the normalization of the data with the light curves. I mentioned that it's like hopefully a big help in stabilizing the image of these quickly varying source. So I also mentioned that in time, the characteristic of the noise looks like red noise, so more energy at lower frequencies. It's actually the same, it seems, in terms of spatial variability. So most of the variability in the source is this sort of change of the entire brightness, not mutual change of brightness between one part of the image and the other. So it's also spatially red noise-like signal, which means that maybe we could really remove a lot of variability by normalizing by light curves. And you can see that here, this is for simulated data. We hope that the simulated data capture these properties well enough. This is the orange curve. What kind of spatial PSD? Now we are talking about the distribution of variability in space, large scale, small scale. And what happens when we normalize by light curve? So the area under the curve, which would correspond to the total variability, is greatly reduced. So by normalizing by light curves, we really stabilize the source, and we give ourselves hopes that what we reconstruct as an image is really a representative image of the average source by removing this intrinsic variability. There is another problem with Sagittarius A star, why this is extremely challenging and why we spent literally 5 years analyzing the data instead of just publishing 4 years ago. And the reason, the other reason, other than variability, is the scattering screen. So somewhere between the source and between us, there is a cloud of matter that is messing our trajectories of our photons. So there are two effects that this scattering screen has. One is diffractive, which is like blurring everything with some averaging kernel. And the other effect is refracting, which is adding a subtle structure on the image, which is related to the intrinsic structure, time varying structure of the scattering screen. So I only got this plot from a paper by Uzao et al. To show you what I mean by this refractive structure. So this diffractive structure is smearing everything, and on the top of that, there was this there was this diffractive structure. So this is a bunch of these small scale structures here. So our imaging algorithm had to also account for that. They needed to understand diffraction and refraction, have a model for this scattering screen in order to be able to tell us what is the most likely appearance of the source from behind this nasty scattering screen. So we needed a complicated pipelines for our algorithm. I will just click for that. All right, so the pipeline for the imaging algorithm looked as following. First step was just being careful with the data, and a couple of iterations where the imaging teams were mentioning problems to people like me working with the data and asking, what is that? Why is this a problem? Is it real? And then I was going back to the upstream pipeline and being a detective, I heard, oh, that's the problem. ALMA wasn't phased correctly and something was blah, 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 this sort of problems. So that was a long step. Then we had a couple of different algorithms for imaging, but before any algorithm was able to touch the data, before we allowed any algorithm to touch the data, we asked all of them to reconstruct different morphologies of the image, like disk, like double to point sources, and such and such. Well, for the obvious reason, we really would hate if our algorithm for reconstructing the image would always put a donut-like shape or a ring-like shape in the data. That would be kind of terrible. We didn't want that. So all those algorithms had to prove that if they are given something that is not a ring, they will be able to see the difference. And then there are, of course, a bunch of tests for all of those algorithms that we use. Well, one is pretty obvious, goodness of fit to the data. Yeah, we need our reconstructions to match the data. That is pretty obvious. But some other considerations that we had were, for instance, how stable is that technique? Meaning, if we change one parameter by 1%, will the image be drastically different? Will it mess up everything? So we don't want algorithms that are so unstable, that have this sort of problem. Okay, so now we have a bunch of algorithms that operate under different principles. We give all of them are tested on synthetic data, and we give them real data. What do we get? This is a little animated story of what do we get. So here you can see different reconstructions of the real data from these algorithms that are already vetted on synthetic data. You can see they're kind of different. It's not very stable. So what we did, we derived a method to define an average image based on these hundreds of snapshots by kind of an automatic morphological clustering. So we asked the algorithm to generate a bunch of clusters of data based on topological properties of the reconstructed images. So these are those 4 clusters, and you can see the frequency of their occurrence here. All right, so 3 are ring-like, 1 is not really so much ring-like. So then we took a weighted average of those 4 clusters, and this is how we came up with the idea of an average image that we believe is a representative property of the source. Now, how important is that? You see that it was kind of important for Sagittarius A star because those individual images were quite different. But if we apply the same procedure to M87, which we did not do 3 years ago, because we didn't feel like we need to do that 3 years ago, the data were nicer, better behaving, and such and such. But if we do employ the same procedure, we get 4 clusters. We really had to ask the algorithm to produce clusters. It would be happy to put everything in a single one if we didn't ask it to make 4 different clusters. So here are 4 different clusters, but they all look pretty much the same, and the frequency of occurrence is the same. So this procedure wasn't really useful for M87. It is, however, some idea of creating a representative image based on thousands of images for Sagittarius A star, where we had variability and scattering related problems. Okay, so that's that much about the imaging. I think there is one conclusion about imaging that is very positive. About 97% of reconstructions have a ring morphology with a diameter of 50 microarc seconds, which is good. This is what we would expect. Our kind of prior. I don't know. If I say prior, that sounds wrong, because it sounds as if we bake that assumption into the methodology. We don't. Forget that I said prior. Okay, so that much about the imaging. Now let's talk about this sort of Bayesian spirit, probability. I wrote NHD under the assumption of GR. Let me explain what I mean by that. We will now assume that GR is correct, that the metric, the space-time metric for this source is a Kerr metric. And we will try to infer something about this source, some properties of this accretion system under that assumption. So in order to do that, we have this huge library of numerical models. And I already mentioned this library to you when we were talking about the structure function slope or PSD slope. But let me describe this library a bit more now. So the very regular part of the library has a couple of dimensions. One dimension is MED versus SANE solution. These are two different types of accretion solution. MED stands for magnetically arrested disk. It is the magnetically dominant accretion flow, where magnetic field is predominantly vertical, and this magnetic field is actually dynamically important, meaning it is directing the motion of the gas. So the gas is not really on geodesic orbits. Magnetic field is important to tell you what is the motion of plasma. Then we have, and on the other hand, SANE is the weak magnetic field solution. So SANE stands for standard and normal evolution of the accretion. Then we have a bunch of spin values from large negative to large positive. Then we have a parameter that is trying to capture all the problems with the dissipation and how the electrons are heated. So this is an ad hoc prescription. It's not a deep theory about microphysics. This is a prescription by Monika Mościbrowska in her 2016 papers, when two parameters, R high and R low, are modeling this distribution of electrons, or really they are modeling what is the ratio between temperature of ions and temperature of electrons. So R high equal to 1/160 or 160 means that the electrons in the disk are 160 times colder than the ions. And unity, value of 1, means that the electrons are at the same temperature as protons. So this is really about how effective they talk to one another and agree about the energy distribution. And this is an open question. Then we have inclination that we test from 10 to 170 degrees. So we look at our model from all the possible angles. We don't know a priori the inclination of Sagittarius A star system. So this is a very systematic, regularly sampled library of over 1 million snapshots for M87 and for Sagittarius A star. And somewhat less systematically, we're also trying to study the impact of non-thermal distributions for electrons energy, tilted accretion disk, and wind-fed accretion model. But I will mostly talk about this very systematically studied library of solutions. And then we have a bunch of constraints coming from the EHT data. So these are constraints such as the size of the object, diameter of a ring that we are getting, its asymmetry, its width, and a couple of other geometric parameters of the image that we are obtaining. Then we also used non-EHT constraints. This is just an upper limit for the quiescent emission at infrared frequencies and X-ray frequencies, and also the size of the source at lower radio frequencies with the scattering screen included. All right, and then we have also this variability that I already mentioned that it's a pain. This variability doesn't want to correspond to data, the variability that we are getting in the models. So this will be another little animation to kind of walk you through the process that we went through. So let's say that these are all our models. It's a part of the library, and we will be scoring them. We will be rejecting models that do not fit our measurements. So here is the size of from the EHT, the size of the feature. Some models got rejected. The shape, like asymmetry of the ring that we are getting. Lots of models rejected. Spectrum, meaning those limits at infrared and at X-ray. And when we add on the top of that the size at 86 gigahertz, we are left with pretty much very small number of models. So there is just few models are able to reproduce the measured properties of the data. And I will talk a little more about their properties in a minute. But let me introduce you to pit subplots. We call these pit subplots, and this is kind of scoring all the models in this main thermal library. So you can see same models on the top, MED models at the bottom, so magnetized, weakly magnetized, spin, large negative, large positive, inclination when you go azimutally through this plot, and air height, so this ratio of temperatures of ions and electrons. And you can see that many models are indeed rejected by the EHT. Red is rejected, green is accepted, yellow is inconclusive. You can see many models being rejected by the EHT constraints, and also non-EHT constraints are quite useful to reject models. So when you combine all of it together, this is what we get. And pretty much all the models, apart from two, are, well, either rejected or disfavored. But when we take into account the variability, all the models that survived, these two guys, are gone because of the variability. So really, there is no model in our whole library of numerical solutions that fits to everything. But okay, let's say that we believe that numerical models can capture the average source property. They only don't understand the variability. And it's not a crazy assumption. Actually, a couple of years ago, if somebody told me that the average properties of the source are obtained correctly with this type of simulations, I would have huge doubts. Now I only have little doubts, because some models do seem to reproduce the properties well. So the second moment, variability, we're not there. Our models are lacking something. So what are these models that are best fitting data? They all correspond to magnetized disks, to a MED solution. They all correspond to low inclination, low temperature coupling, meaning the electrons are much colder than protons, which it's nice because I don't think we had any reasonable proof so far for existence of this sort of temperaturally decoupled, energetically decoupled two-temperature plasma. So there is one, at least in terms of hint, and one with positive spin. And let me just mention this MED system. Now, if you recall this hotspot motion, the paper that I wrote about the orbital motion, so that guy would require MED to behave like that. So this is another suggestion that we are consistent with those different analyses. Both of them are giving us magnetically dominated source. Also low inclination, I also mentioned that with this analysis of the orbiting hotspot. So we are consistent at least here and here. And this is not really constrained by my model of orbital motion. Okay, so the last part of the talk, we will now make this inversion of our Bayesian formula. And now we will assume that our numerical models are good to score data properties, but we will ask, are our results consistent with GR? So it is a consistency test. We will be asking if, given all these models, assuming that there are real possibilities that physical reality is somewhere in between our models, would that imply consistent with GR, meaning with Hermetic? So one thing that we can immediately do is we can take our numerical models, take our synthetic images, and scale them to match our data best in terms of size of the ring feature, and that will tell us what kind of mass of this object is implied by this procedure, by scaling our synthetic data to match the reality, the observations. And then we get an estimate of a mass, 4 ± 1 million solar masses. So it's not a great accuracy. It's not a very precise. It's not a very precise. No, it's not a very accurate measurement. If you compare it to the stellar dynamics, what people do in infrared by tracking stars and calculating mass and distance of Sagittarius through models of Keplerian motion. These are actually the posteriors obtained by Tech group, so UCLA group, and Gravity group. Fun thing is they are inconsistent. This is actually interesting that they are clearly accurate, but somebody is not very precise, apparently. Probably there are some systematics that they don't constrain. But anyway, our measurement is consistent with both of them because they have error bars of like order of magnitude narrower than our error bars. So our posterior, this posterior would correspond to the orange band, this posterior would correspond to green band on this plot, and our posterior is this guy. And I make many panels here because we use different pipelines for analysis, because we are uncertain about everything. So we do different types of imaging and different types of inference. And this is why we have a bunch of posteriors here, another single one. But nevertheless, all of them are consistent with the previous mass measurement. So now we have tested mass measurement. And now I will move to this kind of more GR testing thing. And I will move there using this equation. So let's say that we measure diameter of a ring V. Well, clearly it depends on M over D factor. M is scaling, making the image larger. Larger distance means smaller image. So it is depending on M over D. Then there is an analytic factor in Schwarzschild spacetime that you can calculate on a napkin, really, 6 square root of 3. And then there are a bunch of other things here. So M over D, let's now assume that those guys who are doing stellar models with infrared data, they are doing stellar orbits, they are getting the mass right. Let's use their measurements as priors. This is this analytic component. Then this is the breadth of our different fjords. So we have different models with different parameters. They will give you a different scaling factor here. Then our algorithms are not perfect. Our algorithm will not see the reality exactly. They may be biased in one of our direction. They might be imprecise. So there is another posterior to multiply by. But if we do all of that, and we believe that these guys we can get from synthetic data. So this is the assumption we make, that our synthetic data are really, reality is somewhere in between them. But whatever is left, and if it's not 1, if there is some delta difference, it will imply that we are inconsistent, that something is wrong. Maybe the space-time is different when we assume. Okay, and we can do that. We can do that analysis. And fortunately, or unfortunately, maybe it would be a fun result if we saw deviation from Kerr spacetime, but we don't. So this blue band here is all the solutions admitted by Kerr spacetime. It's non-zero thickness because of spin variation. So 0 would correspond to Schwarzschild, and some deviation here would correspond to maximally spinning Kerr solution. And here is a bunch of our posteriors to compare with that. And again, there are many posteriors because we do analysis with many different pipelines, because we are super uncertain and nobody trusts themselves too much. So different people do different analysis. This is K priors, this is VLTI priors. In both cases, we are very well consistent with a Kerr metric. And you can try and make even a stronger statement and try to translate this delta to a measurement with gravitational waves. And this is, I admit this is a little shaky, because of course they don't measure the shadow size, but they do measure something that is corresponding to a metric component GTT, and so do we. So if we try to cast LIGO measurements on this space of delta solutions, they will also be, of course, consistent with GR. And we have 2 objects, Sagittarius A star and M87 here. So really, we have 10 orders of magnitude of this delta being consistent, this delta parameter being consistent with 0. So consistency with Kerr metric. I think this is kind of amazing. This is really a nice exemplification of what we are saying, that GR is scale-free, and scaling this mass doesn't change the equations. Okay, that's actually, I'm done here, and I will leave you staring at the abyss of 2 black holes that we imaged with the Event Horizon Telescope. Thank you.
Thank you for this excellent talk. Questions? We have questions from the audience. Maya.
Should I go? You can go. Okay.
Right.
So that microphone catches my question. Okay, so first of all, thank you for this really great talk. And I have two questions. So the first one is more hypothetical. So I guess there could be some physical process at play that dampens the variability. And does your team have any hint? What could that be? What's the biggest satisfaction?
Well, theorists have already like 10 different ideas about what that could be. Some people are thinking about non-ideal MHD effects, and for instance, what would resistivity do to that? And I don't know on the top of my head what are the other ones.
Okay, I see. I was curious about like that.
I have already ideas, but those ideas I don't think they are conclusive at this moment.
Okay, and my second question is a small one. It's how do you computationally stabilize the model results so that the images are similar? What you mentioned that the outputs should be robust.
Sorry, can you repeat the question?
Yeah, sure. It wasn't very concise. No, sorry.
It's okay.
How do you ensure that the model results are robust? So I'm just asking about the algorithmic approach here. Do you just compare them?
Yeah, so
gradients
one of the way to do that, well, first of all, there are a bunch of reasons why they shouldn't be too robust. So there is, we make an assumption that these sort of models, and they are general relativistic magnetohydrodynamic numerical models, that they do correspond to reality. But well, first of all, it's not really fluid in this sort of system. It's collisionless plasma. It's a kind of a stretch to claim that we are sure that it does behave according to MHD equations. So there are many reasons like that, that we are not sure. But they are robust in a sense that we have a couple of different algorithms, this numerical algorithm, different codes that perform simulations, that they are consistent with one another. So this is one of the robustness tests that we make. But again, is the physics right? Almost certainly it's not perfect. It's definitely not perfect. The question is it good enough to make this sort of comparisons? And well, it's good enough in a sense that we are finding models that match the data. And I think exciting thing will happen when we really reject all the models and we understand, okay, there is really a huge problem, because when we will learn maybe what we need to add to those numerical models to represent data better. So I'm looking forward to rejecting everything and being absolutely sure that it's all wrong.
Okay, thank you so much.
Thank you.
Other questions?
I have also two questions. One is very practical. Are the light curves from millimeters available somehow that people can download it, or they?
Yes, that's a good question. And it is a very complicated problem because in principle, all of the ALMA light curves are published by ALMA. Everything that ALMA observed is published a year after. Now, this fancy calibration that we made, we so far kept it to ourselves, but we can talk.
Well,
and if you're interested in using them, we can do that. The reason is that there is this big collaboration, and when I leading this effort, if I share the data outside, I am worried that immediately somebody will tell me, but my student was first to do something on those data. Sure. And that's the pain of collaborating with 300 people, all of them very active scientific.
So we can
and all the archival data, this I have it nicely packed in nice folders, and I can give it to you immediately.
Okay, and actually my other question was regarding to you showed the library of models, and some of the models were actually having, I don't know how to say it, but they had like a, I wouldn't say a disk, but some part of the middle.
This one?
Yeah, so there are some of them, like the very middle ones, that we have some outflows going through, like the very middle left, like right, and then for example this one. So what is that going on?
I think here it's an inclination difference. Here you look into the barrel, and here you look from the side. So here you'll see the accretion disk, and here you see a length accretion disk.
Okay, that's.
And this is straight into the black hole from the top along the spin axis. But also, all of those models actually do have outflows. So this is another piece of a puzzle. Why don't we see a jet in Sagittarius A star when we see outflows in all those MHD models? And that's another thing that I don't know. I don't have a good answer for. People say that I shouldn't worry too much because jet should be visible when it hits something, and maybe there's nothing to hit, no shocks to appear. But then I think the galactic center is a pretty messy environment, as you saw. It should be hitting something. I don't know. But that's another. Okay, I'm undermining the analysis here, but yeah, that's another problem of the GRMHD analysis. Outflows are abundant in GRMHD. There are no traces of jet in Sagittarius A star so far.
I have a philosophical.
Oh my gosh.
You have two objects, and for two of them we see low inclination. So their rotation axis pointed us. So for one object, it's pretty improbable to have it pointed at us, just if it's randomly pointed. And for two objects, it's even more improbable. So isn't it worrying?
Yeah, I don't know. That is an interesting, but it's not a philosophical problem. It's a statistics of small numbers problem. Yeah. Well, first of all, I would be pretty certain about the inclination of M87, and this. But then we have a bias in discovering M87 and this black hole because we see the jet boosted toward us. We know about this source so well, and it's such a well-studied source, exactly because it's a low inclination. So, right, so I wouldn't worry too much that, well, M87 turned out to be a low inclination. Now, inclination of Sagittarius A star is a little bit of a puzzle because we are in the galactic disk, and our models want to tell us that we are looking at something perpendicular to the galactic center, to the galactic plane. So this I don't know. But if you recall, I don't know if you were at this slide or did you come a little later. I mentioned this circular stellar cluster with heavy stars, with Wolf-Rayet stars, and this guy is also a low inclination, and this guy is probably feeding EHT. Wow. Also, yeah, it's feeding EHT as well because it pays my salary. So it's feeding Sagittarius A star. So maybe this low inclination is really more related to where is the plane of the disk, and maybe these constraints on the spin of a black hole are not so great. That's just an idea. But maybe the low inclination is really corresponding to what is the feeding mechanism and where is the stuff. With what angular momentum is the stuff trickling into the Sagittarius A star? So I'm not panicking about low inclination of two objects yet.
Yes.
Yes.
Wait for the third.
Yeah, let's wait for the third one. So we don't know of any object in the universe for which we would have the resolving power to see the event horizon. But also, masses of black holes are not always very well constrained. We could be in principle surprised, but I don't think we will. I think that if we want to resolve this sort of shadow feature on angular scale of 10 Schwarzschild radii, or 5 Schwarzschild radii, really. Yeah, okay. 5 Schwarzschild radii. Then I think we will have to go to space. We'll have to put radio telescopes in space, and then we are not limited by the baseline length anymore.
Maciek.
About other objects, and what about Centaurus A?
Oh yes, so Centaurus A, we have a mass estimate, and the shadow size is lower than 1 microarc second, according to this mass. It is nearby object, but it's not a very heavy black hole. It is, I think, 100 million solar masses. Okay. So we made an image of a jet ejection zone with limb brightened jet. And I am working on polarization actually for this data set, but I don't think we have a chance, unless we are 2 orders of magnitude wrong in terms of mass of the object.
Because it's mass estimations from your work, or
no, this is some previous mass estimate. We didn't attempt to measure mass.
Yeah. We think about 1 billion solar masses.
Or you know, as I said, it is not impossible that the error bars are terribly wide. But I think the resolution of EHT for Centaurus A corresponds to about 100 Schwarzschild radii. So if this mass estimate is correct. So it means that if we go order of magnitude to order of magnitude high resolution, meaning we put dish in space, maybe. I mean, I hope for a dish in space, and I hope we will do that. Maybe in 2040s.
Okay, other questions from the audience? Do we have any questions in this one? I don't think so.
So
I think you should click on your because we have a view of.
Alex Marcus.
So do we have a question from Alex?
Yeah. Hi, hope you can hear me okay.
Yes.
Yeah, thanks for giving the talk. I actually just had a real minor nitpicky comment, actually a note of caution regarding the structure function analysis of the continuum light curves that you showed earlier in the talk. So I've done some work with power spectra and structure functions over the years, and the problem with the structure function is that even when the underlying power spectrum is a completely unbroken power law, the corresponding structure function can typically contain spurious breaks and changes in slope. And so I've done, and actually my colleagues at Southampton published a nice paper on this about 10 years ago, Emmanuelopoulos et al. 2010.
Yeah.
So something to keep in mind that the changes in slope do not correspond to anything physical. On the plus side, I think that having worked with structure functions, I think that the estimates of the slopes at the low timescales are likely okay, at least in the limit of good sampling. So at least the left-hand part of the structure functions are usually okay and trustworthy.
Yeah, the point is well taken. Structure functions should be taken with a grain of salt. This is one of the reasons why I didn't jump on making some physical interpretation of this break around 10 or 20 minutes. But let me just give you one comment how we are trying to make our analysis a little more robust. So when we feed a model to the data, a statistical model of some Gaussian process, we draw many times from this model and we calculate structure functions with the EHT sampling on the different realizations of the statistical model. And this corresponds to the light green or light yellow envelopes around the median calculated values. So just why I was talking more about damped random walk rejection is the reason that even when you do this analysis with Monte Carlo, you see that the green line, of course, has a very, very different slope than the observations, right? And so this is one way we are trying to be a little more robust by using Monte Carlo and fitting different statistical stochastic processes and taking different realizations and estimating error bars.
Okay, I mean, I guess my own experience of structure functions is I'd still encourage caution even at the.
Yeah, I fully agree with.
Yeah,
fully agree with the caution.
So tread carefully, Yeah.
Yeah.
Okay.
Okay, I don't see any other questions, so let's thank Maciek again.
Thank you again. To nawet chyba nie przeciągnąłem za bardzo.